Torque is how effectively a force causes rotation. We use the Greek letter tau to represent torque. It's equal to Rf sine theta. So torque is equal to R, which is lever arm, times the force, times the sine of the angle between them. So if we were to think of a seesaw balanced at the middle, that is the axis of rotation. The distance from that axis of rotation to the point where the force is applied is R, lever arm. That's this distance here. The force is going to be the push or pull, or in this case perhaps the weight of the person sitting on the balance beam, the seesaw. So R is lever arm, how far from the axis of rotation the force is applied. F is the force times the sine of theta. So theta is going to represent the angle between them. So the angle between them is 90 degrees in this example. So torque would be R times F times the sine of 90 in this case. So what are common examples of torque? If we were to imagine we're looking down from the top at a door, so where the hinges are would be the axis of rotation for the door. How do we open and close a door? We exert a force, either a push or a pull. Where do we exert the force? You'll notice that door handles are always located at the opposite end of the hinge. Why? Because that gives us a large lever arm. In fact, you would be able to tell a difference if you tried to open a door from a closer point. So if you were to try and open and close a door here, because you'd have such a smaller lever arm, you'd have to increase a bigger force to cause the same rotation. So because we'd have a small lever arm here, we'd need a big force. If we have a big lever arm, we can exert a smaller force to cause the rotation. The angle in both of these cases would also be 90 degrees. What's an example when it wouldn't be 90 degrees? Well, if we were to push at the end of the door like this, the door would not open or close based on this force, because the angle between the lever arm, R, and the force F is 0, or 180 degrees, and sine of 0 is 0. Another example where we wouldn't be able to cause rotation is if we were to push and pull directly on the hinge pin. Nothing would happen if we were to push or pull directly on the hinge pin. So, as you can see, torque is how effectively force causes rotation. It matters. The strength of the force matters, but also where it's applied, what is the lever arm, how far from the axis of rotation, and what is the angle between them. Another example of torque would be different ways in which I could get a bicycle wheel to rotate. So for example, if I exert a force on the edge, the lever arm would be the radius of the circle. So from the axis of rotation to the force, you could see that this would also be at 90 degrees. However, if I tried to cause the same rotation at a shorter point, say right here, you could see the lever arm would be smaller. To compensate, I'd have to exert a bigger force to cause the same rotation. So torque equals Rf sine theta. If I decrease lever arm, I have to increase force to compensate. If I increase lever arm, I can decrease force to compensate. Another example of torque would be trying to open a jar. So when I try to open a jar and I use my hands, I'm exerting a force on the edge of the jar, effectively making the lever arm the radius of the jar, or the radius of the lid, I should say. And you can see that would be a 90-degree angle. Now, if I can't open the jar, I could get a pair of pliers. And if I got a pair of pliers and I use them, well then my lever arm gets much, much bigger. So if I'm using the handle out here, you can see the lever arm gets very big, and as a result, I can exert a smaller force to open or close the jar. And so if I'm unable to open a jar, I could grab a pair of pliers and I would be able to. Not because I can exert a bigger force, but because I can use a greater lever arm to exert the same force to cause rotation. On the next page, we have some practice problems where we're going to use torque. So for example, in problem 1, Bob tightens a bolt on his car tire with a wrench that is 0.4 meters long. If he pulls perpendicularly on the end of the wrench with a force of 200 newtons, how much torque does he apply? Well, again, torque is RF sine of theta. So in this case, it tells me that the lever arm, R, is 0.4 meters. The force is 200 newtons. And it says it's exerted perpendicularly, which tells me that it's a 90-degree angle. So if I multiply all of that out, sine of 90 goes to 1. 0.4 times 200 is 80. I get 80 Newton meters. So that is the unit of torque, the Newton meter. Force, the newtons come from force, the meters come from lever arm. A classic torque problem is the seesaw. So for example, Jack has a mass of 60 kilograms. And he's located 0.6 meters from the axis of rotation, from the fulcrum on the seesaw. Find the magnitude of the torque produced by his weight. So notice 60 kilograms is a mass. So to find his weight, I know the force of gravity is equal to mass times acceleration due to gravity. So if he has a 60 kilogram mass times 9.8 meters per second, I know that's 588 newtons. So when I draw that over here, I can visualize a force that's downward because the weight will be the force of gravity, and it's 588 newtons. So that's the force of gravity exerted on Jack. So how do I use that to find torque? Well, torque is RF sine of theta. So the lever arm, they told us, Jack is 0.6 meters from the axis of rotation. The force is going to be his weight, 588 newtons. And we can see the angle between lever arm and force applied is 90 degrees. If I plug that in, when I plug that into my calculator, I get 352.8 Newton meters of torque. Now you can go ahead and finish the problems on the page using the equation torque equals RF sine theta.